going to talk a little bit more about infinite limits, but more specifically how we know that they result in vertical asymptotes. And so a rule is if a function approaches positive or negative infinity as x approaches c from the right or the left. So if one of those limits, if I say the limit as x approaches c of f of x is positive infinity, right? If the result of evaluating that limit is an infinity, or if as I approach c maybe from the other side, right, from the left side of c happens to be negative infinity, if either of these things are true from either side, then that means that c is a vertical asymptote. If I get a result of a limit of infinity, no matter where I'm looking at it from, then I know that I'm dealing with a vertical asymptote. Right? And that's because it's not defined there. So we've looked at this before in Math 30. So if I want to find the vertical asymptotes of the following functions, you probably could already look at this function, 1 over x minus 4. Tell me the non-permissible value is that x cannot be positive 4, right? That's what would cause me to divide by 0. You can look at that. You can say, okay, that factor is not going anywhere. 4 is not going to work. Therefore, I have a vertical asymptote at x equals 4. Right? You could probably even sketch this function for me. Right? You know that I cannot have an x coordinate of positive 4. You know that numerator of 1 tells me we're probably going to get something that looks like this. These reciprocal functions that we studied all the way back in Math 20. Right? So you know what that looks like. Now we're going to prove it. Now you're going to tell me why you know that that's a vertical asymptote. And as we can see from our little sketch here, we can kind of see those limits as I get closer to that vertical asymptote. As I get closer to 4, I start to approach either positive or negative infinity. And so if I evaluate the limit from either side, let's look at the limit from the left side first. Let's see what happens when I take the limit as x approaches 4 from the left side of 1 over x minus 4. Well, I can substitute in a number that's basically 4, right? A slightly smaller than 4 number, so like a 3.999 kind of deal, minus 4. What that leaves me with is the fact that I have a 0 on the bottom, but it's a 0 that is ever so slightly on the negative side. And as we've said before, if I take 1 and divide it by the tiniest number, it's approaching infinity. The limit of that approaches infinity. Because it's a negative number, it's a negative infinity. And so the limit from the left side is negative infinity. And we can see that right here. Right? We can see that as I get close to this function from the left side of 4, that I shoot down to negative and more negative y values. I'm going to check from the other side. This is all I need. So technically this is all I need to prove that there's a vertical asymptote at x equals 4. But we're going to check both sides just so that we can be super thorough. And I want you to check both sides as well at x equals 4. So let's check the other side. What happens when I approach from slightly positive values of 4? Well, when I plug in something to the right of 4, so like a 4.00001 kind of deal, I'm getting a number that is ever so slightly bigger than 0 when I subtract 4 from it, which means that I'm dividing by something tiny, 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 but positive. And so I'm approaching positive infinity at this one. Either of these is enough to say there's a vertical asymptote. I want you to check both. Just we're practicing those limits, so we're being super thorough with all this. All right, so we can say there's a vertical asymptote at x equals 4. I've justified my answer by showing that at least one of these limits approaches infinity. The big thing here is that I didn't tell you what to look for. You had to use your knowledge from Math 30 to say, hey, I know the potential area where this vertical asymptote could be is at 4. Right. It also tells me a couple of other things. If we think back to LC1 and LC2, this tells me that the limit at 4 doesn't actually exist because these aren't approaching the same value, right? But again, a limit can exist and be a vertical asymptote. It can exist from one side, or they can both be approaching positive infinity, or they could both be approaching negative infinity, but they have to have that infinity component. I also know that this from LC2, if we want to talk about continuity, this is an infinite discontinuity because at least one of those sides approaches infinity. An infinite discontinuity is because of the result of a vertical asymptote. Right, so just other factors. All I care about is that you're showing me these two things to justify that something has a vertical asymptote. So let's look at another function. So here I have x squared minus x over x squared plus x minus 2. First thing we want to do is if we're not provided a limit, again, I need to think about that c value where I want to check and verify the vertical asymptotes. And so that's where we think back to what we did in 30-1. So I'm going to factor. So f of x is actually an x times x minus 1. And then on the bottom there, it's also an x minus 1 times an x plus 2 is going to get me x squared plus x minus 2. Notice I have some common factors. And so when I simplify this thing, f of x is really x over x plus 2. Again, what I know from 30-1 tells me two different things. It tells me that the 0 from that factor that cancels out, it is a non-permissible value, but it's a point of discontinuity, which for us means that the limit exists. It's not approaching infinity from either side, right? It is approaching a value. And we'll calculate that value just for fun. Why not? It also tells us that -2, my other non-permissible value, because it didn't cancel out, is going to be a vertical asymptote. So that's where I really want to make sure I'm checking the limits and justifying that. For the sake, as I scroll all over the place, for the sake of practice, let's check the limit at 1 and just see what happens. We know it causes a problem, but what is the limit as x approaches 1 of this function? And I'm going to leave it in factored form just to make my math easier. Well, I can simplify that. I can take the limit of the simplified form. That's the beauty of this. I can do direct substitution and get 1 over 3. And so what that tells me is that it approaches 1 over 3 from either side of 1, which means it's not a vertical asymptote. There's no vertical discontinuity. It's one of those removable discontinuities in this case. It's that point of discontinuity. And so now I'm going to check the actual vertical asymptote, right? I'm going to do what the question says. Find the vertical asymptote. I knew that already. I'm now justifying why using definition of limits. So left side, right side, we're going to check 2 from the left side. -2 from the left side. Of x squared minus x over x squared plus x minus 2. Now, I can use my simplified form, right? I might as well make my life easy. I might as well evaluate the limit from the left side of x over x plus 2. Cancel out that common factor of x minus 1. So when I plug that in, I just put a -2 on top because that's not causing me any problems, right? It's not giving me a 0 over 0 case anymore because I've done that simplifying. Now, if I'm saying I'm taking a number that is to the left of -2, that's something smaller than -2, which means that I end up with a slightly negative value. Because I also have a negative value on the top, that means that this left side of the limit is actually approaching positive infinity. When I check the right side limit, so I'm still approaching -2, now I'm just choosing numbers that are ever so slightly to the right of that, of my whole polynomial here. Right? Again, I'm going to make my life easy, and I'm actually going to do that simplification before I go for direct substitution, just so the numbers aren't too messy. If I can, I will. So it's still a -2 on top. Now this is like a 1.99999 negative, of course, plus 2, which means that I'm actually going to end up with a slightly positive number on the bottom. Right? When I add 2 to something smaller than 2, it's going to end up overall positive. Because that numerator was negative, though, I'm approaching negative infinity with this limit. Again, I only need one of these two things to make sure that the limit is a vertical, or the point is a vertical asymptote, but I'm going to check both, and I'm going to ask you to check both. So I can say, therefore, vertical asymptote at x equals -2. And so that's how we double check and justify vertical asymptotes.